Welcome to today's video. Today's topic is endianness. You might wonder, what is endianness and why do I care? Well, if you're going to do any type of hacking with a computer's memory, hacking ROM code, and you're going to deal with anything that's bigger than a byte of memory, you're going to need to know about endianness, because while you might not deal with it often, it's going to confuse you when you do, and you're going to be like, what the heck is this? Why am I not seeing what I think I should be seeing? So what is endianness? Wikipedia actually has a pretty good definition, and their definition is: endianness refers to the sequential order in which bytes are arranged into larger numerical values when stored in memory or transmitted over digital links, such as a network. And what that means is that when dealing with numbers that are larger than a byte, so larger than 255, the way the computer stores that number may not be the way you think of that number when you write it out on a piece of paper. What's more is that different computers can have a completely different representation of a number, where they're actually reversed. One computer might be reversed from the other. So when you send a number over the network or in any way into another computer, and you read it into another computer, and if their endianness is different, it will actually read the number wrong, and you'll have a completely different number. And this is often seen when you're dealing with network programming or in ROM hacking, when you look at a memory address and you want to put it like a jump to a memory address, and the memory address looks nothing like what you intend. Then you might look at a memory address and go, that's not the memory address it's jumping to. Well, you're going to see about that today. So let's refresh a bit. A byte is generally the smallest unit that a computer will deal with, which is 8 bits of data. That is 8 ones or zeros in a row. And in a byte, you can store the values 0 through 255. So there's a total of 256 values that can be stored in a byte, because 0 is the first value, 255 is the last. And when we deal with numbers, the way we represent them is generally in hex. So the byte can be represented through the hex number 0 for 0, all the way to FF for 255. Now that's pretty straightforward, but now is where things get a little bit confusing. Generally, we deal with numbers that are larger than bytes. And most times when dealing with computer programs, you're going to deal with something called an integer, or larger. And an integer actually can be different depending on different platforms, but is generally 4 bytes of data, or 32 bits. So an integer represented in binary can be as small as 32 zeros in a row, which is still 0, all the way to 32 ones in a row. And those can store the numbers that we know as 0 all the way to 4,294,967,295. Or when represented as hex, again, all zeros, all the way to FF, 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 FF. But remember, most computers' memory are laid out into a bunch of blocks of bytes, or 8 bits. So an integer requires 4 blocks of bytes to make up the 4-byte or 32-bit number that it's going to store. And those are laid out one after another in memory. And remember, each block or each byte in memory has a special numbered address that refers to that byte or that 8 bits. So remember, an integer requires 4 bytes to store the total possible values. So let's take the integer value 1,122,867, which would be represented as 00112233 in hex. Now, how would we store that into a computer's memory? The way that you look at an integer laid out on a piece of paper, reading from left to right, would be called bigendian. That is, the first byte that you look at on the left is what's called the most significant byte. And it has the most value. Each byte in the series, as you get lower, has less effect on the total value of the number. And that's the way bigendian is represented. The first byte in computer memory would be the largest component or the most significant byte. So in bigendian machines, the number 00112233 in hex would be laid out that way, the same in memory. The lowest byte, at address 0 for example, would be 00. The second byte would be 11. The third byte would be 22. And the fourth byte would be 33. So again, that format is called bigendian. Now the other format is called little endian. And little endian is the exact opposite of bigendian. In little endian, the first byte in memory is what's called the least significant byte. So in address 0, if we're storing this integer at address 0, rather than holding 00, it would hold 33. Address 1 would have 22, address 2 would have 11, and address 3 would be 00. So we store it in memory as we would read it from right to left, from smallest to largest. So why do we care about this? Well, if you're doing work on a PC or a device like an Android phone or old arcade games like a 6502 or a Z80 based system, all those systems are little endian. So when you see a value in memory that's larger than a byte, it's not going to be the value you think about that you see on a piece of paper. It's going to be all flipped. And it's very important you know that, because when you need to edit a value, when you want to hack in some address or some value, you have to actually swap the bytes in memory, because otherwise the value is going to be completely wrong. Other systems, such as PowerPC and MIPS, are bigendian, and they represent the numbers the way you would look at them on paper. So the first number in memory is the largest component, or the byte that's on the leftmost when written on a piece of paper. So what happens when you send a number from one system that is of one endianness to another system that's of another endianness? So let's take the number 1,122,867. In hex, as we read it on a piece of paper, that's stored as 00112233. And in little endian format, it's stored in the computer memory as 33221100. But if we sent that same representation, for example, over the network, to a bigendian system would read that number as 857,870,592, which is a big problem because that's not the number we intended to represent. So hopefully now you understand a little bit about endianness and know the difference between bigendian and little endian. And if you're ever looking at a computer's memory and the number that you think you see doesn't seem to match up what you see in memory, think about this, as this might be your issue.